today we're going to be looking at graphs of velocity and graphs of other functions. We're going to look at the area under those functions and what that means mathematically, and how when we estimate it, we can get an answer that actually means something to us too. There are different strategies we can use to do this that's based on different geometric shapes. Today our shape is going to be rectangles, but we'll move throughout different shapes throughout the week, improving our accuracy each time that we do that. All right. So we did the programs that you need, so you're set for that now. Okay, so I just still need you to have a good understanding from your science classes on how units work. So we learned in first semester that every time we apply a derivative with respect to time, that time then becomes part of the unit. So when we started with a function that was in meters or centimeters or feet or yards or miles, and when we took a derivative with respect to time, the new unit on that becomes meters per second. And then when we take that function and we take the derivative again with respect to time, the new unit then would become meters per second squared. And every time you take a repeated derivative with respect to time, that unit of time increases in power, which again has meaning in a physical world. But so how do we go the other way? Okay, how do we go from, and this is where using your conversion of units and things that you've done in your science classes, how do you go from meters per second, and how do you end up with just meters? So what's the math there?
Multiply by something.
Okay, it's a multiplication problem. You want units to reduce, and the only way to do that is through multiplication. And when you multiply a rate of meters per second times the seconds itself, those units reduce and you're left with back to a unit of meters. So that's how you're going to work between meters or between units in a unit sense, okay, using multiplication. And we'll talk about why that works. So in a physics class, you might be asked a basic question. How far does an object travel over a 3-second time interval if its velocity is constant at 10 meters per second? Okay, so how far is the question? Understanding the question helps you know what kind of units you're supposed to have. So if we want to end up with how far, our answer should end up with meters. In order to get there, we take what we've got, which is a meters per second value, and we'll need to multiply that by a seconds value. And that way the units work out to what we want. So then we take the numbers, 10 meters per second over the time interval of 3 seconds. The units reduce, and I'm left with my units of meters, and then my answer as 30. So geometrically, what does that look like? So I want you to sketch a velocity graph, which would just have two axes. Time is always going to be your horizontal axis, and then velocity being my vertical axis. So velocity is given as a constant of 10, and time is given as an interval of 3. And so we have 3 seconds marked out on our time axis. We have a constant value of 10 marked out on our velocity axis. And because 10 is constant and not changing, then the shape of that becomes a horizontal line. And so overall, I'm left with the shape of a rectangle. And where does 30 come in?
It's the area.
30 is the area, right. So the area is 30, which also matches with the physical, what we were doing in physics. The multiplication matches the geometry because we have a constant value of 10. All right, so say your velocity doesn't stay constant. Say your velocity changes, because it's pretty hard to hold constant velocity. There's always something that's going to be affecting your velocity, unless you're in outer space and in a vacuum or something where you can hold constant velocity, but there's always friction or the wind working against you or other factors that are going to be affecting your geometry, your velocity. So how far would an object travel in 3 seconds if its velocity was changing at 10 minus t per second? How do we figure that out? Well, the math on it is still the same. It's still the units of meters per second multiplied by the units of time to give me an answer of meters. But in this case, I've got 10 minus t and then times 3. So it's not going to be necessarily a constant value. So geometrically, what does that look like? All right, well, again, if we have a velocity graph, and we've got the values of 3 across the bottom, okay, 0 time to 3 time, and then our velocity on the y-axis, and 10 minus t means that when time is 0, what's the velocity? 10. When time is 0, then I start with a velocity of 10. But minus t means I have a slope that goes down 1 over 1, down 1 over 1. So when I have a time of 1, what's my velocity?
9.
So it goes down to 9. And when I have a time of 2, then my velocity goes down to 8. And when I have a time of 3, my velocity goes down to 7. And so this is no longer the shape of a rectangle, but what shape is it? Not a triangle, close. It's a trapezoid, right. So because it's got the slanted top, I guess you could put a triangle on top of a rectangle if you wanted. That would also work. It's a triangle plus a rectangle together. But we also could consider that a trapezoid as well. All right, so now we just need the geometry on that. So my answer should match. The geometry that matches the area of my trapezoid should be the answer to how far this object traveled. So I just need to remember how to find the volume of a trapezoid. So either you know the formula for the area of a trapezoid, or you subdivide it into a rectangle and a triangle and just add them up together. Either way, it should be fine. Does anybody remember the volume or the area of a trapezoid?
This for whom it hasn't taught us this yet.
Area of trapezoid?
Area of Johnson.
1/2 h parentheses b1 plus b2.
We do 1/2 b
Uh,
h1 plus h2 because our trapezoids are oriented the other way.
Yeah.
All right. So we don't just we have a common base, but we have 2 different heights, right? So we got to find the average of the 2 heights. So one of our heights on one side is how much? 10, and the other one is 7, so the average of the 2. Average between 10 and 7? 8.5, okay. All right, so we're looking at 8.5. So our area here is 1/2 of h1 plus h2. So it's the 2 heights, it's the average of the 2 heights times the base. And so in this case, that works out to be 10 plus 7 times a base of 3. So 51 over 2. Okay, that's less. It covered less. It was 30 last time. Now it's 25.5. Okay, 51 over 2. So it covered less meters. Why did it cover less meters? Why physically does that make sense? It's slowing down. It started out at 10 meters per second, but each second it went, it was losing a little bit of its velocity, and so it covered, slowing down. It's losing less distance that it's going to cover. All right, well, that was nice and predictable. It was a nice geometric shape. It was beautiful. It was just a trapezoid. Okay, what happens? Okay, how far will your object travel in 3 seconds with a velocity of 10 minus t squared? Okay, meters per second. How will that work out, and how does that look geometrically? Okay, so we've got our same 10 minus t squared meters per second. Has to be multiplied by 3 seconds, but we're dealing with a variable here. So the question is, how many meters will we end up with? So we need to think of this geometrically again. All All right, so once again, we'll draw our velocity graph. Okay, 0 to 3. When time is 0, the velocity is still 10. So when the velocity was constant, then the top of that just made a nice horizontal line, stayed 10. When the velocity was decreasing, but it was decreasing at a nice perfect slant of -1 with a slope, then we created a trapezoid. What shape do we have coming off of here? Okay, it's upside down parabola. All right, so when time is 1, what is my velocity? 9. Okay, so 10 times 1 squared, so not a big decrease. But when time is 2, what does my velocity drop to? Drops to 6. And when time is 3, what does my velocity drop to? 1. And so now we have not a rectangle and not a trapezoid, but we have a paraboloid that has a straight side, that one straight side on either end. Okay, so this is now a paraboloid. So this is going to be even less distance. I started with a distance of 30 meters. We decreased to a distance of 25.5 meters. Now the paraboloid is going to cause me to have even less because my velocity has decreased by even more. Okay, here's where geometry fails us, because now we're dealing with something that's curved. And so we're a little stuck. We know it's going to be less than 25.5, but how do we figure that out? So this is where, until there was calculus, there was no perfect way to find the answer to this. There was only estimating ways to find the answer for this. Okay? All right. So we're going to tackle this. We're going to kind of blow our picture up. If you liked your picture on the other slide, go ahead and copy and paste it. But I would like to kind of expand this so that we have a little bit more space to work. Okay, so I'm going to redraw mine because I'm not in Notability and I can't. So I'm going to do this. 10, 9, 6, 1. Okay. All right, so the best way to estimate this was to subdivide it into smaller figures. So just like with a trapezoid, you weren't sure if you didn't remember how to do a trapezoid, you could subdivide that into a rectangle and a triangle. Here we're going to subdivide this as well. And we're just going to subdivide it right on the units of 1 and 2. And this is going to be an estimation. Okay? Now, if I take my first one and I say, well, if it was a perfect rectangle, how much would the area of that be? Okay, it has a height of how much? 10, and a base now of only 1. Okay, so this would have an area of 10.
Wouldn't that, wait,
Okay.
doesn't that go to, you looked it up, wait, I'm confused.
I did
Wouldn't
what?
that be 9?
No, because I started on 10 and I went above straight across. Okay, now the next one, I'll go straight across from that and down. That one now is how tall, Rose?
9.
That's 9, okay? And then this one, and if I made that, okay, how much is that one? That's 6. Okay, because remember we did, this was 9, this was 6, okay? All right, so if we add those up, what's the total? 25, okay? Is that, how close is that to the area that's actually under the paraboloid?
Bigger.
Is too much, right? Okay, so we have our first estimate. Let me stick with red. Okay, our first estimate is 25, and we're pretty sure that's going to be too big. All right, now this is kind of where Rose was thinking about. Let's do the shorter rectangles, okay? So let's say, well, what if it only had a height of 9, that first one in there? Okay, if we only do a height of 9, and then this one has the height of 6. And then what would the height of the shorter one be, the last rectangle that I got to?
1.
It would be 1. It would be this baby little rectangle that went over to the other side. So what if I did 9, 6, and 1, and we looked at that area under here? Okay, well, what does that add up to?
16.
16. So my second estimate is 16, and that's clearly too small. Okay, so the actual area that's under the paraboloid, so the real area that's actually in here, is logically going to be somewhere between 16 and 25. All right, what would be a way to improve upon that, to narrow the gap? Because between 25 and 16 is a pretty big gap.
Find the average and then know what, like, based off of the word for it, concavity. Yeah. You can tell whether it's an overestimate or an underestimate.
Okay, all right, you're great. Just thinking, so we can think about an average between the two. That would be probably pretty close to a good estimate. And that is definitely one way that you could come up with it. The Greeks thought about it a little differently. Any other ideas? Okay, and the sigma is just the same, the addition of that, okay? How many rectangles did we make? How many big rectangles and little rectangles? Okay, we had 3 that were too big, and we had 3 that were too small. Okay, one way to improve on this is to have more rectangles. Okay, make your rectangles skinnier. So split all your rectangles in half. Have 6 rectangles. You'll still have 6 rectangles that are too big, and you'll still have 6 rectangles that are too small, but they'll be less too big and less too small, and so you'll narrow the gap a little bit. And that's the way the Greeks approached it. Like, well, shoot, why stop? Let's make 10 rectangles. We just keep making more rectangles and more rectangles. All right, so this is the idea. Okay, what you are doing is called the rectangular approximation method. Okay, so LRAM and RRAM. So let's RAM, and which is the program you have in your calculator, is called the rectangular approximation method. All right, when you put an L in front of it, it means you're working from left to right. When you put an R in front of it, that means you're working from right to left. And going one direction, depending on the concavity of the curve, all your rectangles will either be too big or your rectangles will be too small. So what I've drawn for you here is something that's concave up. Okay, now I want you to look at that. Look at the corners here. If I trace these corners, which corner of the rectangle is it? Is it the left corner or the right corner?
Right.
That's the left corner, okay, of the rectangle itself. Okay, that is called a left rectangular approximation, where the left corner of the rectangle is the part that's touching the curve. As opposed to this one, the corner of the rectangle that's touching the curve is an example then of a right rectangle. But this is concave up. And so in this situation, last time when we were concave down, the left ones were all too big. But this one, because of the concavity, now the left ones are all too small. And then the other way, the concavity, because of the concavity, I can't always say the left, don't ever tell me the left rectangular ones are always going to be too big, just because the first example we ever did was the left ones were too big. The reason the left ones are too big is because the concavity of the graph is downward. But in this situation, because the concavity of the graph is upward, all the left-hand ones are too small. But if the left-hand ones are too small, then the right-hand ones are too big, or vice versa. It all depends on your concavity. Okay, this is an example of a parabola going up. All right, so we're going to try it on a graph that has a little bit of both. Look at how I picked this one on purpose because I have a tiny bit of this graph that is decreasing, and then here's the vertex, and then going up the rest of the way. Okay, so I'm going to try this one with you. All right, the directions are make an LRAM and an RRAM approximation of the area under this particular parabola, who is concave up, but its equation goes x squared minus x plus 3. And I've given you the values over here on the little chart. Okay, so go ahead, and we're going to use nice intervals that are already, so based on those intervals, how many rectangles will I be able to draw? 6. All right, so the way you indicate that is like this. You say, I'm going to do an L, I'm going to do left rectangles, and then you put a little 6 there to say that you're doing 6 of them. All right, so go ahead and just put little dots on the places where your intervals intersect. And I worked from left to right, and don't include the last one, because we're only working from left to right when we're doing our LRAM. Okay, so working from left to right, I draw my first rectangle straight across from that dot. Okay, perfectly horizontal. That first rectangle is too, what? Big or small? That one's too big. Okay, what is its measurement? What is its area? 0.5 on the bottom. And I gave you the chart on the side, so how tall? Times 3. Okay, so the first one was 1.5. Okay, now working from left to right, so do the next one, and just from that next dot, go straight across. Now that rectangle is too small. What's its height? Okay, well, how long is the base? Still 0.5. And how tall is it, according to the table of data I gave you?
2.75.
All right, so what is that? Okay, 1.375.
Thank you, Christian.
If you did it without a calculator, it would be non-decimals. Okay. All right, and then we do the next one. And we go straight across. And that makes another rectangle, which is too small. But what is its area value?
Let's see, that's 2.
Back to 1.5 again. Why? Because what are the bases are always 0.5. And the height on this one is back to a height of 3. All right, and then we'll do the next one. Straight across. What is its height? According to the chart data I gave you. It's 3.75. So then what is the area? Well, 0.5 times 3.75, which is, you guys have your calculator sitting on your desk. Go ahead, figure it out.
Oh,
It's just multiplication. It's just base times height, base times height, base times height. 1.875. All right, next one. Remember, we need 6 of them. Okay, and then the last one. All right, so somebody can figure out rectangle number 5, and somebody else can figure out rectangle number 6. All right, what's rectangle number 5 turn out to be? 2.5, good. And rectangle number 6? Good job. 3.375. All right, now add them up. Okay, let me know if somebody gets one.
12.125.
12.125, okay. Overall, for that total, would you say that that's likely to be too big or too small?
Too small.
Why?
Because most of them are small.
Most of them are too small. Okay, but why?
There's more area that under the curve that is empty and not in the rectangle than over the curve.
Okay, why?
Because the concavity is.
It doesn't have to do with the concavity, because this thing is all concave up, and what part of the section was above? Okay, even it was still a concave up section. Doesn't have to do with the concavity.
The window.
Something else about the graph. Okay, well, what's different about the section right here, which had the only one that was too big? What was different?
The slope.
Okay, the slope was doing what? Decreasing. And here,
Increase.
okay, it was increasing, right? Because the slope was increasing and concave up. That is why all of those things are under. It's not just because it's concave up, it's because most of the function is increasing and concave up. And that leads to the left, most of them being under. The only one that wasn't was the one that was decreasing but concave up. All right, so you gotta have a good reason of why it is. All right, now we do our RAM, we go the other direction. We work from right to left. So I'm gonna pick a different color, I'm gonna pick red. And starting with right means I start with the highest one. And I do a rectangle from there going across from that. And so that's clearly gonna be quite a bit higher than that other one. And then working right to left, again, I'm gonna go across and down. And then what about when I get to my last one? Okay, the one that's, if I'm working from right now back to left, when I get to here, what happens to the top of that rectangle? Or where is the top of that rectangle gonna be? It's gonna be under, because I'm working from right to left. And so it was the smallest one of all. So 5 of those rectangles are all overestimates, and the last one is an underestimate. And so that would be an RRAM 6. And we add up the values of that. Now we can probably do this a lot faster because this rectangle here, this smallest one, is the same size as this one, the second one here. So we know its value, right? How much is it? It's the same as this one right here. Okay, so it's 1.375. And the next one would be the same, 1.5, and then 1.875, and then 2.5, and then 3.375. And the only one I actually have to figure out for myself would be the tallest rectangle here, which has a height of how much? Based on the data table I gave you. 9, and a base of half, and so its area is 4.5. Okay, let's add those up. Aren't you glad they invented calculus so we don't have to do this all the time?
Yeah.
Okay, but this was as good as they had it. Anybody think of a fast mathematical way to do this so without having to add all these up? Okay, so 12.125, which was all these numbers, but which one are we not using? We're not using 1.5, so what could you do? Take away the 1.5, and then which one do you need to add in? 4.5, which is adding a net total of 3. So adding a net total of 3 to that would be 15.125. So you don't even have to use your calculator. All right, and we know that that one is too big. So we have one that was too small and one that was too big. Nothing that was just right, like Goldilocks. Okay? All right, so look at the difference here. These are the different situations that you would have. If you have increasing with positive concavity and left rectangles, you'll always be underestimating. If you have decreasing with positive concavity, left rectangles will always be overestimating. If you have increasing with positive concavity, right, these are the right ones, right rectangles will always over. But if you're decreasing with positive concavity, right rectangles will always underestimate. Those are your situations. Not even drawn negative concavity yet, just the opposite for all the negative ones. There are questions so far? Yeah.
But because it's a parabola, so it's like the perfect reflection on each side, wouldn't you be able to take the average at like both of these?
Oh yeah, so you're jumping ahead to average. You're getting to tomorrow's lesson. Yeah, we're gonna be doing that. Let's just focus on left and right for now, but yes, we will be doing that. All right. So last one. A car is traveling down a straight road. All you have is a table, no graph. Use the average of RRAM and LRAM. So let's do LRAM. Let's just start. We'll do them in order. This is our last thing. Can you do it without drawing the rectangle? If you made a rectangle using this data, and the data went from 0 to 7, what would, if you were using the left one, which of the velocities would you be using? The value of 30 or the value of 36? Left one, can you picture it? It's 0, 30 and 7, 36. Which one's higher?
36.
The 36 is higher, so the left rectangle is going to be base of 7, height of 30. But the right rectangle would be a base of 7, a height of 36. Okay, what would the next rectangle be? Let's just finish. What would the base of the next rectangle be if you went from here to here? Base of
36.
Base of 5, height of 36, and a base of 5 with a height of 43. Just want to make sure you're understanding. What's the next base?
8.
8, good. 8 times 43, 8 times 48.
And that's because the t is just the x value, right?
Right, the t is the x value, but I didn't make it even, right? This is not even. They're different all the time.